Morning, Precalc. It is a lovely day out. It's a nice fall day here. I'm recording on the, 29th of September, I think, but this lesson's for sometime in October for you guys. So we're going to talk about finding all the zeros of polynomial functions, not just the real ones today. But we're going to start out finding the possibilities of all the rational zeros. Now, rational, remember, means can be written as a fraction. So rational includes, 2, -4, 1/3, 7/11, etc. Okay, 0.5. So we have nice decimals, nice fractions, anything that can be written as a fraction. It does not include crazy, even repeating fractions work, repeating decimals, I mean, but no square roots, okay, and no imaginary numbers. So recall that the polynomial function of degree n can have at most n real zeros. Real zeros can be rational or irrational. To find the rational zeros, okay, meaning they can be written as a fraction, there is a theorem that says when you have a polynomial, all right, you can find all the possible, that's the important word here, all possible rational zeros. They won't all work. And you find them by taking the factors of the constant term over the factors of the leading coefficient. All right? So if I had 6x squared plus 2x minus 11, I'd have all the factors of 11 over all the factors of 6. And those would be all the possible ways that I could get the real solutions. So, or the, I'm sorry, rational solutions. So I'd have plus or minus 1 or 11 over, now 6 has more factors than that. It would be plus or minus 1, 2, 3, or 6. And then we'd have to write all those out. We're going to practice on the next page. Okay, this one over here says exactly the same thing. It's in the terms that your book used. All right, so it says using the rational zero theorem, list all possible. So it means you have to write them all out for me, rational zeros. So this one is plus or minus the factors of 40 over the factors of the leading coefficient is 1. So that's pretty easy. What divides evenly into 40? We would have plus or minus 1 goes in 40 times. We'd have 2 goes in 20 times. We'd have 3 doesn't go in, but 4 goes in 5 times. No, 4 goes in 8 times. Wow. Okay, there's mistake number 1 on this video. 4 goes into 40. Let's try that again. 4 goes into 40 10 times. 5 goes into 40 8 times. Guess I shouldn't be thinking about whether they're all going to fit or not. You can write them in any order you want, but those are all the possible rational zeros. There aren't any fractional ones for that because the coefficient was 1. Over here, we have all the factors of the constant back here, 28, positive or negative factors of 28, divided by all the factors of the leading coefficient, which is 2. Now, you don't divide this out and get 14, okay? You need all the factors, so I'd have plus or minus 1, 2 goes into 28, 4 goes into 28, 4 goes into 28 7 times, 2 goes in 14 times, and 1 goes in 28 times. I think that's it. And down here, we'd have plus or minus 1 and 2. Now, you need to write them out for me. Must write out. So you need to tell me, because there's numbers on top and numbers on the bottom, you need to reduce that for me. So if you put them all over 1, all you get is 1, 2, 4, 7, 14, and 28. Every one of those should be positive or negative. I'm just going to be lazy and let you be lazy and not write them all out, but you could have 1, 2, 3, 4, 5, 6. That's a total of 12 numbers you could try. And then we need to put them all over 2. So if we put 1 over 2, we get 1/2. We put 2 over 2, we get 1. That's already on our list. 4 over 2 is 2, already on our list. but 7 over 2 is not on our list anywhere. 14 over 2 is 7, already on our list. 28 over 2 is 14, already on our list. So we ended up with 1, 2, 3, 4, 5, 6, 7, 8, or a total of 8 times 2 is 16, total of 16 possible rational zeros. Now, this has at most 4, but there are 16 possibilities. Okay, it doesn't have to have 4 rational zeros. Some can be irrational. All right. So when we get to a question like this, it says list all the possible rational zeros and determine if any are zeros. So our constant is 6, our leading coefficient is 1, so we have plus or minus 1, 2, 3, what else goes into 6? Just 6, okay? Those are our only possibilities. Now, you can graph for your second step to determine which one, if any, of those work, okay? The other option would be to start putting numbers. Back in the day when I didn't have a graphing calculator, I just start putting 1, 2, 3, and 6 in here, or doing synthetic division with each one until I got a remainder of 0. We have a graphing calculator, so we throw this thing in the graphing calculator, and we see that it has a 0 at -2. Now there's another 0 in here and another 0 in here, but they're not integer values, okay? They might be rational, but they're not integers. They don't come out nice. So we're going to go with the one that came out nice, which was -2. So we put the 0 of -2, and we do synthetic division. 1, -5, -17, -6, no zeros needed or placeholders. Bring down, multiply, add, multiply, add, multiply, add. So we end up with a depressed polynomial, this is called. I don't know if I used that vocabulary before, but the remainder is called the depressed polynomial. He's sad, anxious, depressed, right here, this guy. We know how he feels, right? Welcome to COVID. X squared minus 7x minus 3 is what we have left. We know there was also an x plus 2 factor because of this -2. Now, the problem is this doesn't factor any further, and it actually, we have to do quadratic formula to find the 2 remaining zeros. So we have A is 1, B is -7, and C is -3. Opposite of B would be 7 plus or minus the square root of. All right, we're supposed to square -7. Can I just write 49? Because that's what -7 squared is. And then it's -4 times 1 times -3, which is going to turn out to be plus 12 all over. Let me move this guy out of here. Okay, or not. All over 2 times 1, or 2. So we have 7 plus or minus. This is 49 plus 12, which would be 61 over 2. Let me scooch that up. So this is all over 2. So the zeros were at -2, and then 7 plus the square root of 61 divided by 2, and 7 minus the square root of 61 divided by 2. All right, if I had my calculator still on with that graph in it, I could go ahead and go trace and then type parentheses 7 plus the square root of 61 parentheses divided by 2, and it should jump right to an exact 0 on that graph. All right, this one is actually way easier than it looks, okay, because list all the possible rational zeros. Well, we already did one with a constant of 20, I think, and no leading coefficient. So we'd have plus 1, 2, 4, 5, don't forget 10 goes into 20, and 20. So there's all the possible rational zeros, okay? Now, determine if any of them work. Well, if we graph this bad boy, guess what? You have to test. You have to go trace and test, but it turns out -2, 2, and 5 all work, I think. So what we're going to do to prove that is we're just going to pick one of them. I don't know, let's try 5. You can pick any one you want to go first. And then you do the synthetic division. Bring down, multiply, add, multiply. Be careful, this is where I usually make a mistake. 5 times 0 is 0. Add is -4, -20. Okay, if it doesn't turn out with a remainder of 0, we did something wrong. All right, now we have to think about what this depressed polynomial means. We had a factor of x minus 5 because of this guy, but this is, let's see, -4 is a constant, 0x and 1x squared. So we have x squared minus 4. Well, guess what? That factors x minus 2 and x plus 2. And the zeros are then at 5, 2, and -2, just like the graph showed. Okay, so you could have basically done that one as a graphing problem. The other thing is, just a hint, anybody remember we could have taken an x squared out and had an x minus 5, and then taken a -4 out of these back two terms and had an x minus 5. This one happens to factor by grouping. As a possibility as well. All right, polynomials can have zeros that are complex. Now, complex number system includes both real and imaginary numbers. All right, a polynomial function of degree n, where n is greater than, has at least one zero in the complex number system, because any real number is also a complex number. So anytime you have a polynomial, linear or above, quadratic, cubic, anything, there's at least one zero in the complex number system, because it means there's basically a real number is also complex. So there has to be at least one zero. All right. A linear factorization says if c is a complex zero of a polynomial, then x minus c is a linear factor of the polynomial. Well, I just did those linear factors on the last problem, okay? It turned out x minus 5, x minus 2, x plus 2. All right, all polynomial functions can be completely factored. The problem is they don't all have linear factors, okay? We're going to now find the complete factorization of the function. Over here it states that polynomial, it's the same thing. It says degree n has at least one zero, real or imaginary, in the complex number system. In fact, it has exactly n zeros, but that includes repeated zeros. They don't have to all be original. They can be repeated zeros. So here's an example using fancy factoring. It says x to the fourth minus 24x squared minus 25. All right, our fancy factoring, when there's an x to the fourth and an x squared, we factor the x to the fourth as an x squared times an x squared. And then we look at negative 25. We would have 25 and 1. To get a negative 24 in the middle, you'd need more negatives. So it would factor like this, okay? Then if we set each of those equal to 0, this one actually factors further. And this one does not factor further, but we can solve it. Whoops, there's a 1 in there. So we get x squared equals -1, and then when we square root both sides, we get x equals, remember it had a squared, so it's a plus or minus, and the square root of -1 is I. So we could also write those as factors. It's always x minus, and then positive I, and x minus negative I, which would turn into plus positive, and then we had an x minus 5 and an x plus 5. So we found all four zeros here, and we found all four linear factors in any order here. I don't know, yeah, linear, they're called linear factors because it's degree 1 of x here, even though that's not really a line because it's imaginary. Okay, the conjugate root theorem is super important, and it's just kind of slid in here, but it says that whenever a plus bi is a 0, then a minus bi is also a 0. The same is true if you had like a plus the square root of b, a minus the square root of b would also have to be 0, okay? These come in conjugate pairs, whether they're rational or imaginary. Excuse me, irrational or imaginary. All right, so it says, finally, to go over this one more time, you would list all the possible rational zeros, test using synthetic division, or our hint is to graph. And then when you find a zero that works, use the remainder to completely factor the polynomial. Okay, so we're going to use synthetic division, and we're going to divide successively, meaning once after the other. If we have to, most of the time we'll be left with a squared quantity that either factors or we can use quadratic. But if we happen to get a degree 4 or 5, we're going to have to divide successively, or one after the other. Consecutively, I guess, kind of works too. All right, let's go to the next page. Here we go. All right, so this one, all the factors of 2 over all the factors of 1 would simply be plus or minus 1 or 2 over plus or minus 1, which when we write out is just 1 over 1 and 2 over 1. So these are the only 4 possible rational or nice zeros. Now, if I think about this graph, it is a cubic shape with a positive coefficient, so I should know it's going to do this. So it has to cross the x-axis at least once. All right, I go over here. Oh, it's actually this side that crosses the x-axis, and it crosses it, looks like at 2. Now, if I still had this in my calculator, I would go trace 2, enter, and make sure it came up exactly 0, because sometimes it misleads us. But this one does have a 0 at 2. So then we do synthetic division, 1x cubed minus 2x squared plus 1x minus 2. Bring down, multiply, add, multiply, add. 2 times 1 is 2, 0. And this is constant. This is a linear term, gets an x, 0x. And this is a squared or quadratic term. We have x squared plus 1 as what's left. And this was an x minus 2. All right, is that a linear factorization yet? Unfortunately, no, because this still has a quadratic. But does that factor nicer? Well, definitely doesn't factor. And if you look over here, it actually doesn't have more than one real 0. So there's going to be some imaginary zeros. So if we set this equal to 0, it's actually the problem we just did. Square root both sides, we get x equals plus or minus the square root of -1, which is I. So we had an x minus 2. We had a 0 at I and a 0 at -I. So if I do x minus I, and this one would be x minus -I or plus I, now I have the linear factors, okay? I'm also supposed to state the zeros, which were at I, -I, and 2. So there's the 2 things we're looking for, the zeros and the factorization. All right, I think this is our last one. Yep, one more. We are going to type that, well, first of all, let's list the possible, because this one does have a leading coefficient, so this is good practice. So we have the factors of 5 over the factors of the leading coefficient, which is 2. We got to list these carefully. We would have 1 over 1, 5 over 1, and you don't have to put plus or minus every time. I'll let you get by without. And then put 1 over 2, and then 5 over 2. All right, now there could also be imaginary zeros. And I graphed it, and it looks to me like there's 3 real zeros. It's degree 5, so it could also have 2 imaginary zeros. Whew, This is going to take us a minute. So the first thing I did was it had a 0 at -1. So if I do -1 into 2x to the 5th minus 5x to the 4th, we need some placeholders. There's 0x cubed or 0x squareds in there. So this is a tricky one because we have some zeros. There's no x cubed or x squared, so we had an x to the 5th, x to the 4th, x to the 3rd, x squared, then an x to the 1st, and a constant. All right. This is supposed to come out 0 if we do it right, because we know this is a 0 on our graph. So we bring down 2, multiply by -1, add is -7. I almost put 7. Okay, multiply by -1 is 7, add is 7. -1 times 7 is -7, add is -7. -1 times -7 is +7, add is 5. -1 times 5 is -5, and it comes out 0. Whew! But look at this mess that we have left. Okay? We have a mess left here. We need to figure out what else works in this polynomial. I'm hoping I have this one left on my screen here. Yes, this is the right one. So I need to figure out what else. Oh, it looks like +1 works. And this actually looks like it's between 2 and 3. And on our list here, 5/2 would be 2.5. So while I'm here, I'm going to try 2.5. And that is a 0 as well. All right, so we checked on the graph, and +1 should also work. Whoops, let me write that in a better spot. I'm going to put up here, +1 worked. Okay, so bring down the 2, multiply, add, multiply is -5, add is 2, multiply, add, multiply times 1 is -5, add, and we get a 0. Oh, this would actually factor by grouping, I bet, because you see it has a common factor here of 2 and 5. We could, if we wrote it out, it would be 2x, let's see, this one doesn't get an x, this one gets 1, 2, 3, 2x cubed minus 5x squared plus 2x minus 5. We could take an x squared out of these two. And to put these in a parentheses, we would take out just a 1, and then it would factor. But I'm going to go with what we did on the calculator. We actually said we saw that 2.5 worked, which is 5/2. You could write 2.5. I'm actually going to write 5/2. So if I bring down a 2, think about that for a minute. 5 divided by 2 times 2 would just be 5. Add and I get 0. Multiply by 0 and I get 0. Add and I get 2. Okay, 5 divided by 2 times 2, again, is 5. Add and we get 0. So now we have what's left is 2x squared plus 0x's plus 2, which we can take a 2 out of, and we have an x squared plus 1. And then we wrote up here these three, x minus 5/2, x minus 1, and x minus -1 or plus 1. All right, are we done? Are these all linear, guys? The answer is no. By the way, you cannot lose this 2, because if I start multiplying this all back together, it has to go back to be what we started with way up here. Okay? So it has to have a leading coefficient of 2. But some of you are smart enough to realize we could have distributed the 2 through here and written that as a 2x minus 5, and then we wouldn't need that coefficient out there. All right, before we finish though, we got to solve this guy. X squared plus 1 equals 0, means x squared equals -1, means x equals plus or minus the square root of -1, which is plus or minus I. Wow, these all came out very similarly, didn't they? All right, So the zeros we found, this does not count. 2 does not equal 0, so don't use that constant out front as a 0. The zeros we found here were I and negative I. Over here we had 5/2 or 2.5 because it's exact. You can write it as a decimal. I'm going to leave it as an improper fraction. Over here we had 1 and negative 1. So those are the zeros. Now we're supposed to write the linear factors. I'm going to squeeze them in up here. We would have x minus I, x minus negative I, or plus I, x minus 5/2. Now, you can write it that way, okay? But you're going to have to put the 2 out front if you do that. And then x minus 1 and x plus 1. Out of room. Last minute of the video and I run out of room. Okay. Some of you are smart enough to realize that you could have distributed the 2 through here and made that factor 2x minus 5 because that would be 5/2, and then you wouldn't have needed the 2 out front. So you'd have an x minus 1 and x plus 1, and then you'd still have times the x minus I and the x plus I. Well, that's a hot mess because I ran out of room again. All right, that's it for the first part of this lesson. So you're asked to find the possible rational zeros, graph it, figure out which ones work, then do your successive divisions until you have imaginary solutions or complex solutions. Remember, we had to do quadratic formula on one. Those were irrational, sorry. And then write it all out with linear factors and find all the zeros. All right.